it is my pleasure to come home, if I may say. And I have nostalgias about the weather, I have to tell. So I think what I will do, I will talk about a topic which covers the past and goes into the future, because we had some recent results which are pretty interesting, and we are planning nice things for the future. So let me start with a phrase I just heard on a symposium, and it stuck into my mind. The phrase was, vision without funding is hallucination. So actually, there are some people who are sitting here who made sure that LIGO is funded. So the way I would phrase it on the LIGO way is that vision without detector is hallucination. And I would like to make sure that we all understand that this talk is totally impossible without the data which was provided with many people by the LIGO Corporation making and building the detector. So I would like to be very grateful to them. So what I will do today, I will first tell you about the past results, and then show you how future detectors can enhance what we have right now. So many of you have seen this slide in many colors, in many versions, and many talks. Yeah? So these are the promises of gravitational waves and what will happen when we will detect them. What happens is that if you scrutinize each point here, you will very quickly realize that most of these promises, most of these interesting points are connected to cases when we have other observations available beyond gravitational wave observations, or matter of fact, some of them are possible if we use other observations. For example, the wave propagation speed and others. So if you look at this slide, then you start to feel why I'm so excited when I think about multi-messenger astronomy. We use other channels beyond gravitational waves to actually get information about the source or the waves or general relativity itself. So I recommend you to look at this slide many times, and you will see that multi-messenger observations pop up at many places. So if you think about gravitational waves, there are many ways to characterize them, many ways to put them into little boxes to think about them. There are boxes which are motivated by more sociology. There are boxes which are motivated more on signal characteristics. So here is an ad hoc characterization of the gravitational wave sources. The way I look at them, I can distinguish three major categories based on the type of the duration of the gravitational wave. So in my mind, there are transients which happen once for a short time. This can be, say, signals related to gamma ray burst. There can be repeaters. There were relatively little work done on these sources. These are sources which produce gravitational waves repeatedly. For example, this can be eccentric encounters when two compact objects, like two black holes, scatter on each other, and at the closest approach, you have a burst of gravitation coming out. This investigation shows that you can lose enough energy in gravitational waves that you can actually get into a bound orbit and come back again and produce gravitational wave burst again and again. And that is, for example, a repeater. I highly recommend that you listen to the talk of my colleague who will give the LIGO seminar, I think a couple of days, John 11. She has some very nice ideas about this kind of source. So I will not talk a lot about this, but she's very good. And then there are continuous sources where the signal is available for a long time, and you have to integrate for a long time. So this is just my way to look at the case, because it gives me some easy navigation points in this phase space gravitational wave signals. So when you want to define this view and you want to look at the fine structure, then you can think about gravitational waves as modeled, where model is available, or unmodeled, or triggered. We have this lingo we call the search triggered when we have a sky position and timing available, for example, or we can search for all sky and all time on the sky. There are various groups devoted to these activities, and all of them are doing very nice work, and there are some publications out detailing the results. So I think the recent one is on the spin down limit of the Crab pulsar, but I think the common venture of the spiral CBC group and the burst group is also very interesting. And I will elaborate on this one just to go closer to the topic and discuss. So if you look at this kind of compartmentalization of the field, you will realize that many of these compartments can be addressed through multi-wavelength astronomy and can be actually used in coincidence with astrophysics observations. One ingredient which is necessary to actually have a common observation schedule with the astronomical observatories, observatories, and neutron observatories is the direction. Yeah? So beyond providing us with increased confidence, we also need gravitational wave detector networks to have a good pointing information. So if you see here on this world map, then what you see is that we have the two LIGO detectors in North America. We have the Virgo detector in Italy, and we have the GEO detector in Germany and the Gamma detector in Japan. Right now, we are concentrating on the three large detectors as a common network to provide directional information for the future. So these detectors have finite bandwidth. You probably all know this sensitivity plot, where you see on the x-axis is the frequency of the gravitational wave, and y is the noise, and here is the prediction of the noise sources. This is the sensitive volume, and you see that we are roughly sensitive in the 100 Hz to kilohertz region with the present detector. And to reach this sensitivity took us a lot of work. And if you see, this is where we started with the detectors, and many iterations later, hard work, we reached the design sensitivity of the detector, including most of the frequency range. If you see, this pink is the design sensitivity, and the red fuzzy line is the S5 sensitivity as it's reached. So what I will tell you about is a result, actually two results, which are obtained from the data taken during the 5th science run with roughly the design sensitivity of the detector. So if you think about multi-messenger observation, you might ask, why are we bothering about multi-messenger observation? Why don't we just use the gravitational wave data alone and have the result? If you think about it and think concretely about multi-messenger observations as gamma ray transients, including gamma ray bursts or soft gamma repeaters, or optical transients or neutrino events, what you get is correlation in time, correlation in direction, and maybe some information about the source properties you can use in the search to make your search more and more sensitive. This means that you can have a more confident detection of gravitational waves, better background rejection, higher sensitivity to gravitational wave signal, and maybe more information extracted in case of a detection. So these are all good motivations for multi-messenger searches. And if you think about it, within the field, there are a large number of publications on this topic, so there is high interest. And most of the interest is concentrated on the gamma ray burst channel. So what I will do first, I will talk a little bit about gamma ray burst and the related gravitational wave observations, and then we can go to other channels. So Probably this is known for most of you. Traditionally, gamma ray bursts are classified as short and long bursts. Short bursts are something below a couple of seconds, and long bursts can last for hundreds of seconds. Yeah? And there are recent evidence that long bursts can be classified further. However, as far as we are concerned, the main point for gravitational wave physics is coming as a side product of the short-long classification of the gamma ray bursts. Why do I say that? I say that because in spite of the fact that according to the leading picture about gamma ray bursts, we end up as a black hole central engine providing a highly energetic jet, giving us this gamma radiation as a result of the collapse. There are two ways to reach it, either through a binary in spiral or a core collapse of a massive star. So what happens is that it doesn't really matter whether you get a long gamma ray burst through a core collapse, which is the leading progenitor, at least our belief to this, or a short gamma ray burst, which is coming from the binary spiral of compact object, where one of the objects is a neutron star. We are dealing with a source where there is significant chance for gravitational wave emission. We know that the compact binary objects are the leading candidates for gravitational wave detections, and we know that core collapse supernovae are also very interesting for the field. So in a sense, GRBs are interesting for us. There is another source which is a little bit different from the others, which is a so-called soft gamma repeater, which is believed to be a highly magnetized neutron star. These are very rare galactic objects, at least we know it in the galaxy, and this can actually emit fair amount of gamma radiation, and it probably provides some fraction, maybe less than 15% of the short gamma ray burst population as observed. And as we will see, there are some chances that gravitational waves are also interesting in this context. So when we look at this picture, we see that regardless of the mechanism, we have some common interest with the gamma ray physicists, and whenever we see gamma ray bursts, we better try to follow them up in gravitational waves. So we are not alone in that belief. We are writing a review article, and when we did the literature search, cursory literature search at the beginning, turned up about 121 plus papers on the topic. So this is kind of a hot topic, how to relate gravitational waves and gamma ray bursts. And I can guarantee that I didn't find all of them at that time. So there is more than 121. So we have the scientific motivation, we have the interest from the theoretical and experimental communities. Question is, how many gamma ray bursts are coinciding with the LIGO data taking periods? Can we really do science with these? And if you look at the statistics, about 70% of the GRB triggers during the fifth science run coincided with at least double interferometer data taking, and some of them were short duration GRBs, which is very important because if you remember, significant fraction of the short GRBs are associated with the binary source, which are very interesting for us because we can see them from far away. And unfortunately, the 25% with measured redshift were probably too far away for our interest. So we are interested in the remaining 75. Yes, it's kind of counterintuitive, where we have a chance that they are close by. I think we have all the ingredients for the witch's brew, and we just have to find the right instance to exercise our searches. And we had actually a couple of very nice cases when we got lucky in a sense, and we could do some science with gravitational waves and gamma ray bursts. So the first one is this GRB, so-called 070201. And we had a nice paper, which was a beautiful collaboration between the burst and the inspiral groups of the LIGO scientific collaboration. And it was really a nice experience to have this paper. And let me try to share the suspense with you as we followed this. So we had this notice from our friends in the gamma ray burst community that there was an observation for a GRB, an intense short hard GRB. You know, this raises our blood pressure a little bit, and it was at a place on the sky which was okay for our detectors. Not the best, but not the worst. So there are, you know, other short GRBs. So why this one raised our blood pressure a little bit more than the others? The reason was that the error box reconstructed by our gamma ray burst colleagues coincided with a very famous galaxy, which is M31, or Andromeda galaxy. And this galaxy is about 770 kiloparsecs away. Matter of fact, we just had a little paper written about this distance. I didn't know that. We don't know that distance so well. It was an interesting study. But the important thing is that if this gamma ray burst really happened in the Andromeda galaxy, then we are in a win-win situation. So that's why we were so excited. What happens if it is binary in spiral, which might be 85% of the cases for short gamma ray burst? If it is really binary, then it should emit strong gravitational waves. And we know enough about our detector to suspect that 770 kiloparsec is really close enough to catch it. Yeah? And if it's a soft gamma repeater, then, well, we know 5 of these in the galaxy. And this is extragalactic. So in the worst case, this is an extragalactic soft gamma repeater. And that's also sort of an interesting thing from astronomy. So regardless of what we find, it's interesting science. Yeah? So, matter of fact, after the analysis, some of our astronomer colleagues looked in the error box behind Andromeda. And actually, there's a better error box which is smaller, still centered on Andromeda. And what they have seen is that there's very little matter in that error box far, far away. It's kind of hard to look behind a bright galaxy, but you can actually have a feeling that there is very little matter. So that's the case. So what happened? We exercised 2 kinds of search, one model dependent, other model independent. The model dependent search was targeting binary in spirals, where one of the companions were a neutron star, the other was either a neutron star or a black hole, and we covered a large range of masses for this heavier companion, and then we set lower limit on the distance, yeah? Because we found no plausible gravitational waves coinciding with this source, so we had no other choice than set lower limits. If you look at this plot, this number signifies parsec, means that with 90% confidence level, a low mass system must have been at least 3.5 megaparsecs away to get missed. Yeah? So this means that if something was really at the distance of M31, we would have seen it regardless of the companion mass with 99% or more confidence level. This means that we can really exclude the possibility that it was a binary at Andromeda. So what remains open, whether it was a soft gamma repeater in Andromeda or a binary behind. That's why our astronomer colleagues look behind the galaxy to see whether this lower limit, 3.5 megaparsec, really means a much larger distance. Yeah, because if there is no material behind the galaxy in that error box, then the lower limit is really larger up to the closest galaxy. So that's actually interesting paper which is coming out. So the model-independent search had the same result with a little bit less confidence. They excluded M31 as a source of a binary. So what remained for us is to see whether the model-independent search can address the soft-gamma repeater scenario. And if you look at the energetics of the soft-gamma repeaters, then you see that you are talking about energies in the order of 10 to the 45, 10 to the 46 ergs. So if you scale the sensitivity of present LIGO detectors and you look at the exclusion region, everything above these lines are excluded by the model-independent search as a function of frequency. What you see is that even at the best frequency, we can't exclude below 10 to the 51 ergs. This means that our search is really consistent with the soft gamma repeater in Andromeda scenario, the extragalactic soft gamma repeater scenario. So, you know, it's an interesting case to contribute to some suspicion about the first extragalactic soft gamma repeater. So that was interesting. However, during the fifth science run and before that, other interesting things happened with the galactic soft gamma repeaters. So these sources, there are 5 of them. Each of them has a different number, actually signifying sky position. This tells you that there are really few of them, because we are not afraid to have 2 of them in the same direction. One of them had a huge hyperflare before the 5th scientific run, when we were roughly factor of few less sensitive than during the 5th science run. And that excited our interest in these objects. And as we learned more and more, we interacted more and more with theorists in the field, then we realized that these are really interesting objects. What happens is that soft gamma repeaters are either perceived as highly magnetized neutron stars with huge magnetic fields, or there are some alternative models when they are perceived as solid quark stars. And this is interesting that it's very hard to distinguish between the 2 scenarios with conventional methods. However, one of them could give you much stronger gravitational waves than the other. And that makes these interesting. Just because if it's a solid quark star scenario, the crust is a lot stronger. It can support a lot more strain. So we looked at these objects, and first of all, during the hyperflare preceding the S5 run, people discovered a very interesting phenomenon that in the tail, after the initial gamma ray burst detected, in the tail, people have seen quasi-periodic oscillations in the X-rays. And some theorists and some observers associated with these oscillations with the seismic motion of the star itself. So we looked for this signature in gravitational waves, and what we got was quite interesting. Our upper limits, when converted into energy, for example, here, this is our upper limit, and this is the observed energy in electromagnetic waves, are in the same order of magnitude. So we realize that here is a source, and we are having limits, upper limits on the gravitational wave emission, which is in the same order of magnitude as the electromagnetic emission from this source. And we had this with data which was not even design sensitivity of LIGO. And then, you know, people started to think about this, and the conclusion was that theorists are interested because, you know, this source are getting interesting if the gravitational wave emission is in the same ballpark as the electromagnetic emission. So this really made us interested in the topic, and we followed up with analysis of, you know, hundreds of SGR flares, weaker than this hyperflare, but many of them during the 5th science run, and the PRL on the topic just came out. And if you want to know the details of this, there are people here at Caltech who can explain it For example, I think Peter Kalmus will be able to help you with that. Actually, I borrowed this slide from him. And the bottom line was that the best limits we could place on the emission of gravitational waves from this source were in the few times 10 to the 45 ergs region. And this is for a source which is order of 10 kiloparsecs away. Yeah? And if you remember, the electromagnetic radiation of the giant flare was in the 10 to the 47 erg region for the electromagnetic radiation. So this is getting interesting. Yeah? We didn't get lucky because we didn't have a giant flare during S5. But if we would have one, that would be really interesting because this is much below the electromagnetic energetics of that object. So in the meantime, there were some theories published, and it seems that this limit with this electromagnetic, even with this low electromagnetic emission, is starting to address and limit with some of the theories. And if you look into the future, then what you see is that if you look at the figure of merit, what we call gamma, arbitrary name, that the ratio of the electromagnetic energy and the gravitational wave energy, and you compare it for the 5th science run, which is the past, 6th science run, which is the enhanced LIGO run, which will come next spring, and advanced LIGO, then for the optimistic scenario, case 1, if there is another giant flare from SGR 1806-20 at 10 kiloparsec, then the S5 data would have allowed us to go about a factor of 50 below the electromagnetic energy content of this source. S6 will probably allow us to go more than 2 orders of magnitude, and advanced LIGO will allow us to go below this electromagnetic emission with more than 3 orders of magnitude, which is really getting into the interesting region of limiting theories. And even if there is a typical giant flare, we can still get below the electromagnetic emission. And there are many extensions to this scenario. For example, there is a new SGR discovered, and the beauty of that SGR is that instead of 10 kiloparsecs away, it is maybe 2 kiloparsecs away. Yeah? And our energy limits in gravitational wave go as the square of the distance ratio. So 5 times closer means 25 times better energy limits. So if we have a close-by source, it can give us much better results. We are also pursuing interesting extension to the analysis, because if you think about these soft gamma repeaters, this is not like any other gravitational wave source you would consider, which happens once and then doesn't happen again. What happens is that this is potentially a repeater, because what it does, it's the same neutron star gets excited and emits a gamma ray burst, and then later emits it again and again. And what happens if each of these emissions is accompanied by a similar gravitational wave? Since you are ringing the same bell again and again and again. So the idea is that we can stack them. We can just take, this is a so-called storm from SGR 1900 plus 14. You can take each gamma ray burst and handle it as a trigger, and then pile the gravitational wave data on top of each other and search in a cumulative data, where the noise goes down and the signal gets enhanced. So you gain by the square root of the number of bursts you are taking into account. So you are potentially getting an order of magnitude for each 100 bursts in this sense. So this is an ongoing investigation which can actually dig deeper into the noise. So getting an order of magnitude in energy is a pretty good goal. So it's pretty clear that in the past there were some interesting insights associated with the gamma ray bursts and other external triggers. And our goal is to enhance this scientific endeavor and actually extend it to better and better analysis, better and better science. And let's see what is the future with enhanced and advanced LIGO. So conventionally, people display the reach of these advanced detectors in the future as, this is the LIGO coverage, this is the enhanced LIGO coverage, and this is the advanced LIGO coverage. And this sees incrementally larger volume of the cosmos. And, people are really excited, and I think if you ask Alan, his group, the compact binary coalescence group, are really excited because there are dozens of detected, even predicted, based on astrophysical models. I'm excited with my colleague Jenna because maybe we will have some ecstatic encounters with this repeating source. So this is an exciting era for gravitational physics. So what can we do with multi-messenger observations? So let me just change a little bit to a different topic, which is very exciting for us right now. And this is actually different from gamma ray burst, at least for the first sight. But when we look at this problem more closely, we will realize that this is not too much different. So the idea is that ultra-high energy neutrinos can travel from large distances from extragalactic sources and may be associated with the same progenitors, same basic engines as gravitational waves. And it's beautiful because beyond the gravitational wave detectors, we have ultra-high energy neutrino detectors in the northern and southern hemispheres, and all of them have some kind of pointing and timing resolution. So maybe we can use them together and try to do science none of them can do alone. And that was the promise. And when we started to look at the problem, we realized that, this looks pretty interesting. Because unlike other messengers from remote engines, high-energy neutrinos and gravitational waves are really travel cosmological distances. There are no deflection by magnetic fields, which would probably cause problems with charged particles. And they can actually escape from dense objects, as we will see one of the proposed sources imply. So ultra-high energy neutrinos and gravitational waves are interesting. And TV. Mm-hmm. The thing is that they are created probably later, according to the model. Yes. Sure. Yeah, but you are traveling with the speed of light towards you, so you don't really care where you create them in the line of sight. However, the point is that you might not learn about the source physics from the neutrino. However, what you have is a confident detection of a source. You have the timing and the direction from them. And what you can have is really a much lower detection threshold than you could have any other way. Yeah? You can have a single ultra-high energy neutrino significant when you do it together with gravitational waves. Yeah? So that's the name again. Yeah, the problem is that you don't have extragalactic reach for them. Yeah? So no, actually we do have extragalactic reach. Not for supernovae. However, gamma ray burst, binary compact in spirals, we have extragalactic reach. Matter of fact, if you look at the distances, the gravitational wave reach and the feasible rate of ultra-high energy neutrinos from these gamma ray burst sources are not matched. Yeah, but I agree that supernovae is let's see, opportunistic. So if you look at the possible sources for ultra-high energy neutrinos and gravitational waves, then it's the literature search and interaction with the theorists turns up really interesting things. We learned that long GRBs, those can be associated with high energy neutrinos. Short GRBs can also be associated with ultra energy neutrinos. And low luminosity GRBs with potentially fairly large population can also be associated with ultra high energy neutrinos. So I listed some of the references here. There is more. Actually, what I would like to emphasize also that there are sources where you can't really learn about the source from automatic observations because those don't produce so much gamma radiation, like it's called failed GRBs. Matter of fact, you have a local expert on this, one of our collaborators, Shinichiro Ando, sitting backstage, second floor. These are very interesting because these are sources which are hard to observe in anything but high energy neutrinos and gravitational waves. So we have a source here which is hard to observe electromagnetically, but the gravitation with neutrino observation together can turn up and observe a source which is kind of hidden other way. So there is a very exciting science case for this. And if you look at whether there is available detector, then you see that IceCube at the South Pole is already operating with a partial network, which is pretty good already, and Antares is already operating in the Mediterranean Sea. So if you look at the history and the future of these detectors, then you can easily realize that in the past there were some common data taking period for LIGO, Virgo, Antares, and IceCube with, admittedly partial network for the neutron detectors, but these are still able to provide actually 1.52 degrees direction and decent timing information on the neutrinos. And in the near future, during the enhanced LIGO run, you actually have much more Antares strings, and we expect much more of the IceCube detector completed. And who knows what's happening in the future. There are interesting extension in the radio to IceCube and so on. So the future seems to be bright together for the detectors. And the nice thing about Antares and IceCube, that beyond sensitive to the same phenomena, they are covering sort of the northern hemisphere and sort of the southern hemisphere. So they are complementary. So we have IceCube detection rate is, who knows? The number of neutrinos they see, not necessarily from cosmic sources, is 10 or 20 a day, depending on your threshold. So in a sense, there are single neutrinos which are coming with a rate of 10, 20 a day. And the interesting thing about it is that there can be a cosmic neutrino among us, but it's very hard to tell about a single neutrino whether this one was right and the other 9 was kind of a background. That's why if you use together with the gravitational waves, you can have an interesting selection effect.
So when you say 10 or 20 a day, that's pretty all background, or how much is it?
Probably all of them are background. Yeah.
Do they have any events at all that are
that would be a big splash if they would have it. Yeah. So that's why it's interesting, because in a sense you need multiple neutrinos from the same source to have some point source recovery. Yeah. And if you use another detector coincidentally with this single neutrino, as Yoichi and authors on that paper showed, you can actually have interesting false alarm rate for the common observations. So first, only the LIGO, 2 LIGO detectors and IceCube analysis was scrutinized. And if you see this circle, this is the point spread function of 2 LIGO detectors. Why? Because you only have time for flight, so the source is somewhere there on the sky. So you need more gravitational wave detectors to have more than a ring. And if you combine this ring with the point spread function of the single neutrino from ice cube, you get some interesting result. But you get much more interesting result if you combine a fictitious LIGO-Virgo detector network, and the point spread function is kind of interesting. And I have full hope in Anthony to produce a better point spread function with his glorious new methods. So, but it's pretty. So I like this one. So this is a point spread function, and I have to thank Yoichi for that. And if you combine this sky map with ice cube, then you get a very interesting formula. What is the basic line is that this, I think you like this kind of formula. You have many of these in publications. If you look at, say, 1 gravitational wave trigger a day, 20 neutrinos per day, and some coincidence window, then the false alarm rate for coincident detection, false identification, would be 1 in every 600 years. This means that if you see 2 of them together, you really should be suspicious. What's going on? Is this a real thing? So this false alarm rate estimate really, increased our excitement about this topic. Yeah. So of course.
The 1 second window. What's the 1 second window?
It's kind of an apt choice. 1 second. It can be model dependent. Some models, depending on which model you use, it can be longer. What did you say?
We're not sure how the delay there is in the in case of short theory, there might be but we don't know.
Yeah. So that's one of the control. So that parameter is in a sense a model dependent parameter. So probably the search in a sense can be something between full directional search or directional and timing search, depending on the model and the parameter. However, if you take this hypothetical scenario, then what you see is that instead of having discovery quality, threshold size for gravitational waves, for example, you have a fairly small threshold for gravitational waves, and for neutrinos, you are really handling a single neutrino instead of requiring some coincidence. So in a sense, at the price of introducing some model dependency, you enable the 2 experiments to do something together what they can't do alone. So that's an interesting aspect.
So for current models of gel-produced neutrinos, how far out can you go and expect to see one?
They can come from far away. Question is, what is the rate? Yeah.
Well, the
Because it's quantized, so you either get one or not. Yeah. So depending on, people talk about megaparsecs. Yeah. So it is kind of matched to the gravitational wave source, but it also fairly model dependent. Yeah. But you can catch one. You can catch one from very far away. The question is whether how often do you catch it from the source? So when you go far away, you start to compete with the population model, because when you are far away, you are just not getting it. So it's kind of fuzzy line. So after a while, it becomes luck dependent. So we are aware of many questions and many potentials. So I use it use this opportunity for shameless advertising. So we are organizing an international workshop exactly on the topic, ultra-high energy neutrinos, gravitational waves, to bring all the experts together from neutrino theory and gravitational waves. And it will be in Paris, May 18 to 20. Set aside the date, please come. And I think we convinced a fairly wide set of people to actually give us advice on the science of this topic. So we have really high hope that we can mine this topic scientifically in the near future. So I guess I'm running a little bit out of time, so I will kind of mention an interesting topic. I strongly recommend that you invite some other speaker on this one. This is also multi-messenger observations. If you imagine, you can do the opposite, what I was just telling you. Instead of taking triggers from the outside, you can just identify the location on the sky and the time of gravitational wave triggers, and then you can do observations on the sky and see whether something is glowing. Optical follow-up. Yeah? So you can do this for gravitational waves, and there were some pilot projects done. Here is one of the observation schedules, and I think there will be significant work done on this range sometimes in the near future, and there are many people who can give you very good talks on this. And the future is bright for both Earth and space-based gravitational wave physics. So I just put up the concept of the LISA project. I guess you are much more familiar than I am with it, so I will not even attempt to describe it for you. And I would like to emphasize that beyond the advanced LIGO, there are visions for future gravitational wave detectors on Earth, and this is the concept for the Einstein telescope, or ET, in the European Union. This is just artist rendering, and this would be about a factor of 10 more sensitive than advanced LIGO. So there are some plots what you can prepare based on first principles. These are just to guide your eye. There is no deep content in them. You are just scaling the sensitivity curves, and these are courtesy of Jones from Cardiff. And what you see is that if you are looking at the Einstein telescope sensitivity to neutron star and some companion in spirals, then you can really go into the far reaches of the universe. So in a sense, there is a very high promise for coincident observation of gamma ray bursts and gravitational waves in the even advanced LIGO, but ET is definitely a very promising tool. You can do this exercise for equal mass systems, which is very similar, or you can do this exercise for unmodeled gravitational bursts, or in this case, for repeaters, so gamma repeaters, and then you see that ET should be able to reach the extragalactic SGR we were just discussing. The others will probably only have galactic reach. And if you look at just the energy for some source where 5% of a solar mass is released in gravitational waves, then you also have a fairly substantial reach for this future detector. So this is really an encouraging prospect, and I'm really happy that I put my life on this endeavor. And this is just advertisement for supernovae. If you want to learn more about supernovae, then probably it will be a different speaker. And this is the end of my talk. And I think this is great exploratory science. We already had some interesting scientific results. And enhanced LIGO and advanced LIGO is coming. And it is a very interesting teamwork. Many people contributed, and we are tough. We survived the fire and flying police. is the conclusion, and I would like to thank all the people who helped us making the hallucination into vision at Columbia, and I show an old picture about the group, and I'm very proud that we have a cross-section from high school students to successful undergraduates, graduate students. Old picture, Peter is already here, and as you heard about his SGR-related work, so Harald said about the details, he's standing there, and Yoichi is also in this picture, and he's already working on the 40-meter and LIGO hardware. So it's interesting. It's a nice place, and I also have to thank all of my colleagues in the LIGO scientific collaboration. It's a big group, but it did something interesting. Thank you very much for your attention.